My name is Karin Hing, and I'm going to give you a little bit of a talk today about sort of use of materials engineering in developing new biomaterials and medical devices for use in bone regeneration. So, for want of a better description, I've called it engineering better bone. Okay, and I will crack on. So, right, get it over here. There we go. Right. So why am I even working in this discipline? So how did I get here? Probably more luck than judgment. So when I was doing my A-levels, I had no idea what I wanted to do. I didn't know whether I wanted to do chemistry or physics, and I decided to do materials because it was a mixture of the pair of them, and I didn't have to make my mind up. So I then ended up working on an industrial placement with somebody who was about to start a PhD or start as a lecturer at Queen Mary and offered me a PhD here in something that was called the Interdisciplinary Research in Biomedical Materials. So I ended up then doing my PhD in biomedical materials purely by chance, and have loved it because it gives me a chance to play both with chemistry, physics, and also biology as well. So and a bit of engineering as well. So the nice thing about working in this sort of field is it gives you a chance to do something that you feel like is actually being used to actually help people in the real world. So it's quite nice and rewarding to be able to go out to hospitals and talk to surgeons and discuss with them about whether or not something you've had a hand in developing is working and bringing benefit to patients and sort of stuff like that. So it's quite good from that point of view as well. Okay, so how has the field evolved over the scary amount of years that I've been involved in it? It's moved quite a lot. It's moved from sort of pure engineering days of thinking about, right, we're dealing, in my field, we're dealing with bones and they're strong and therefore we need to think about making strong engineering materials to fix them, into thinking more about it from a sort of actual biomedical engineering or tissue engineering point of view, where we're actually recognizing that we're dealing with a living substance and that we need to develop materials that are a little bit cleverer than we first thought we needed to develop. And that's some of the things I'll cover in a bit more detail in this talk. But so the whole movement of the field, materials development, has been really important. Yes, yeah, it is. At least I hope so. Yeah, no, there's a little. Yeah, it says it's being recorded. So, yeah. Okay, so so yeah, sort of materials development has been really fundamental. So one of the things some of you might have in your third year is you might be being taught by me in the third year, and I do Science of Biocompatibility module. And that's all about how we understand biocompatibility, and we use our understanding of what makes a material or a device biocompatible in a specific application, and how to try and manipulate the materials and use engineering to design better structures in order to elicit an appropriate response from the biological host. So it's involved a lot of change in the way we think about materials. So over the years, we've sort of gone from thinking, oh, something that's inert is great because we can bob it in and we don't need to worry about there being any sort of nasty reaction. And now the thinking is more that we want things to be bioactive. We want things to, in some applications, integrate with the local host tissues and the cells and actually be part of the biological healing response. And we don't even think anything's inert anymore. We've realised there is no such thing as inert in the body. Everything has some sort of response. So we talk about things like alumina and being near inert. Okay, so what has our role been in the sort of development of materials over the years? Well, we started off back as a PhD student with my PhD supervisors, Serena Best, Liz Tanner, who some of you all know, and also Professor Bill Bonfield. We started off really just with trying to understand the effects of varying materials, chemistry and structure when they were used in bone replacement on bone regeneration. So in the infancy of the field, there was a sort of a understanding that some materials were good and some materials were bad, but no real understanding of what made them good and bad. So we applied that knowledge then to engineering a new type of synthetic bone graft substitute that was able to rapidly stimulate bone regeneration. And that resulted, in the development of some materials that are now used clinically. So for us, materials engineering has been about combining basic science with also more applied real-world applications as well, to try and bring the two together to actually sort of do your basic science, and then you think about how can we actually use that in the real world to actually, be useful to other, be of more interest and use to people outside of academia, basically. So how to put that out there. So one of the first things we had to do back in the day when we were first thinking about things is recognise that bone isn't there just for its strength. It's actually a very remarkable living tissue. So it's got both load-bearing and heliostatic or endocrine type roles. So it's involved not only just holding you, being there to make sure you're not a jellyfish and you don't flop on the floor when you try and get anywhere. Your bones act as the sort of anchorage for tendons and things that allow you to move around, because that gives you sort of, ability to lever yourself about. And it also has sort of so-called homeostatic or endocrine roles. So there are a lot of hemopoietic stem cells, blood cells, a lot of hormones and things are generated within the marrow cavities of bones. And that's only now really being fully understood and recognised and being realised as a key role of your skeletal system. So unsurprisingly, throughout your life, your skeletons are not just when you're growing. Now, even my skeleton, ancient as it is being constantly renewed. So within me, there'll be these sort of remodeling cycles going on. So as I run around and do silly things, I don't know, skiing and stuff, then I will put microfractures into my bones, and the cells within my body, are so specific ones like osteocytes and osteoblasts and osteoclasts, will recognise that internal damage and then work together to resolve. So the osteoclasts will resolve away the bits of broken or slightly damaged bone, and then repair that. The osteoblasts will come along, they'll signal to the osteoblasts to come along, the osteoblasts will come along, deposit some new unmineralised tissue. That tissue is then mineralised, and then the sort of damaged piece of bone will have been restored. So that's going on all the time. And on top of that, somebody like Andy Murray, who while he's playing tennis is clearly using his forearms a lot more and getting a lot more impact in his forearms than me, he will have a much higher bone mineral density because his bones will have used what we call their mechanosensitive abilities to be able to realise that they need to be stronger than they might be naturally, and so therefore his bone density and probably actual bone mass will increase significantly. On the other hand, someone like Tim Peake, when he goes up and plays around in the space station, will lose bone mineral density because he's no longer subject to the same gravitational forces that he is when he's on the Earth. And actually one of the big, you don't hear Elon Musk talking about this, but one of the big issues that actually acts as a proper scientific barrier to space exploration is how to keep people from being jellyfish by the time they get anywhere in several hundred years. It's going to take you several hundred years or 50 years or whatever, depending if you can invent spacewalk time machines to get ourselves from one part of the universe to the other. If you're out in a gravityless situation for any period of time, your bones will gradually resorb away. So understanding the mechanisms that are controlling these processes is actually quite important from the point of view of being able to enable us to explore space properly. So if we can work out what's going on and how to override those mechanisms, then we can make sure people can retain their bone density while they're out in space. So back to this planet. So fixing broken bones. So the top 3 fracture sites are the hip, the wrist, and the spine. And unfortunately for us, not all bone fractures will spontaneously heal. So, bone is able to repair itself to a certain extent, but if you get something like what we call a critically sized defect, it means the defect's too large for the bone to spontaneously fix itself. And this sort of failure of bone to repair itself significantly impacts quality of life. So if someone has a protracted fracture that won't spontaneously heal. So you can imagine something like this, sort of like fairly catastrophic fracture of the femoral neck in the hip. You know, that person's not going to be able to walk around. They're going to be in significant pain. So these sorts of things have significant impacts on quality of life. So there's a lot of different ways that you can try and fix a bone, and a lot of different materials that are used in fixing bones, and that reflects the vast range of different sorts of roles that bone has in different parts of the body. So there are some places like total hip replacement where strength is key, and you can only really replace those components with materials and devices that are going to be strong and tough and have a reasonable fatigue life as well. Similar sorts of things, bone screws and plates, although there are some instances where you might want to put a bone plate or a screw in temporarily to initially fixate a fracture site for then spontaneous healing to occur. And you don't necessarily want to go back in there and take that plate or those screws back out again once healing has been achieved. So there's also a lot of interest, and so we're working here on some development of new bioresorbable materials that have adequate step strength initially, but then are resorbable under more controlled conditions, as cell-mediated resorption as opposed to pure physiological resorption or corrosion, in order to then be able to design devices that could be used in those sort of applications. But the thing I'm going to concentrate on today is bone graft substitutes. So estimated around 2.2 million orthopedic procedures a year involve bone grafts. And the bone graft substitute market is estimated to reach around $2.3 billion this year. So there's quite a bit of money in it as well as it being something that, you know, you're trying to do for the greater good of humanity. So what is a bone graft? So it's basically a material that's used to promote or assist healing. And I brought some, I don't know, post this the COVID days, I don't know if we're allowed to do this sort of things, but I brought some with me for, I don't know if you want to pass them about or let people have a play. But so bone grafts, basically, they're materials that are used to promote healing. When do you need it? So you need it so if the defect's large or unstable, so in sort of critical defect type site, or if bone, one of the things that bone really needs is an ability to be stable. So that's why when you break your leg, you're put in a cast. So it stabilizes bone ends and allows spontaneous healing to occur. Micromotion is the enemy of bone regeneration. So if the defect is particularly large or particularly unstable, you might need to put a graft in there to help promote the healing. You also have situations where the patient's bone biology is compromised, and sadly for people like me, that means when you get old. So as I get older, there's more chance that my bone won't spontaneously heal if I do something stupid. And then the other sort of major area where you might need to use a bone graft isn't where there isn't any bone. And this is particularly relevant in spinal fusion. And spinal fusion is one of the big users of bone graft substitute material. So in a spinal fusion operation, what you're trying to do is you're trying to get these vertebrae to fuse together. And you usually do that by creating bony bridges across this area of the vertebrae, rather than trying to get bone fusion across the sides of the vertebrae. And sometimes you can put in devices in as interspace disc spacers, and you may have bone graft substitute in there as well to promote fusion directly through the base of the discs. So in these sorts of areas, you're actually trying to get bone to grow where it shouldn't normally be. So you need something like a bone graft substitute in there, so that it acts as a sort of a bridge or a scaffold for the new bone regeneration to occur across what should be a joint, so in order to fuse those vertebrae. So traditionally, people used to use autografts and allografts as bone graft substitute materials. So hopefully this isn't going to put anyone off their lunch. So autografts are where bone's actually harvested from the patient. So the normal place to get it is the iliac crest of your pelvis. So this is still in some cases considered to be a gold standard because it's got everything you already need. It's got the patient's own live cells and growth factors in there, and it'll undergo cell-mediated remodeling, i.e. the osteoclasts and the osteoblasts that are programmed to repair bone will look at it, think, oh, it's a bit of bone, I don't know if it should be here, and repair it effectively, remodel it to produce new solid bone in the implant site. The problem with it is obviously limited supply, major issue with it. Obviously, if there's only so much bone you can get out of your iliac crest and use elsewhere. So in something like a multi-level spinal fusion, there probably isn't enough. And then there's this sort of so-called socio-economic cost. So one of the things that can be a massive issue sort of in long-term, sort of the long-term health of the patient is that after the bone graft has been removed, then you can end up with what we call donor site morbidity at the donor site. So obviously this chunk of bone is taken out and this bit doesn't spontaneously regrow and reheal, and you end up with basically a defect now in the pelvis. And that can result in long-term chronic pain for the patient. So they get rid of one issue only to get another one instead. Because it's a second operative procedure, there's doubles the infection risk at the operative site. And it also means that the patient has to have extended time in theatre, which isn't good from the point of view of the healthcare authority, because that means it's going to cost them more. And extended time in hospital, which isn't good from the point of view of the patient, because they want to get out of hospital as soon as they possibly can and get on with their lives, because they're having to recover from two different operative sites. So allograft, and this is rather nicely demonstrated here. So allograft is where you're using bone from donors. So these can be, as in this case, a cadaveric bone that's been retrieved from someone who's left their body to science. And then that's chopped up, morcelized, sterilized, processed and various things, and then packed up in bags. And people can use that then in other operations. So with this one, there's increased supply, or not unlimited, obviously, but a greater supply than what you can get out of somebody's pelvis. And it will also undergo cell-mediated remodeling. However, with this one, there are disease transmission risks, and this was a particular issue when, for instance, CJD evolved and became an issue because the material wasn't being processed originally at stringent sort of protein and prion killing type protocols. So they were concerned that maybe allografts were potentially spreading CJD. There's also issues with variable bioactivity. So again, you're getting bone from donors, you've got no control of which bones you're getting. If you get a nice piece of femoral head or tibial plateau, then you might have lots of nice cancellous bone in there, which is great for bone regeneration. If you end up with a bit of somebody's skull or portions of their ribs, that'll be much denser and it won't be anywhere near as good for bone regeneration. And that sort of goes to variable consistency. So it's a bit lucky dip. You never know quite what it is you're going to get. So, hooray! So what's the answer? Synthetic bone graft substitutes, where we make things as we want them. So the basic requirements of a bone graft substitute is it needs to have adequate strength, and you want it to encourage and support bone regeneration. So the early bioengineering view, when I started first working in this field, was really concentrating on the adequate strength. Everyone's like, bone is strong, we need to make bone graft substitutes that are strong, because bone's load bearing. And I spent a lot of time trying to work out how to make hydroxyapatite porous structures that had dense struts, and hydroxyapatite is the material. I could talk a bit more about what that actually is later, but it's a very difficult material to work with because it decomposes if you get it too hot. So you can't use normal sort of materials processing techniques of I want to make a microstructure dense, so I'll just whack the temperature up. You whack the temperature up on HA, it just decomposes and becomes things that aren't bioactive anymore. So, so the early view was really, we need to make it strong, and we need it to be tolerated by bone tissue. So bio-inert will be okay, actually. We don't really need it to be bioactive. And so people were like, well, let's stick some alumina into some HA, or maybe we can use alumina, which is aluminium oxide, sponges, and there was all sorts of things that we were playing with. So the first generation of synthetic bone grafts then were great from the point of view of supply. So you could order these up and they'd come by the bucket load. But the bad things about them were quite a lot. So there were almost as many bad things about them as there were different types of bone substitute that you could get. So one of the worst things really was there was a real bewildering array of chemistries, because there was no sort of thinking that you had to have a bioactive material. Some of these materials were made from aluminium oxide, some of them were made from porous ceramics, other porous ceramics like porous zirconias. People were using things like porous polyethylene as well, so sort of inert polymers, and there's all sorts of random things. And they had very different macrostructures. The macrostructure is the sort of if you've got a little bone graft substitute, it's the pores that you can see. So sort of a millimetre in, or so a millimetre, half a milli in size. So the macrostructures were variable. So again, from one material to the next, you've got a different porosity. And then also the microstructures were variable. So you can imagine, using a scanning electron microscope at much higher magnification, looking at what the structure is of those little struts that you can see in the bits of bone graft. Some of them had porosity in them and some of them didn't. And this sort of range in strengths, range in structures, range in microstructures meant that the materials that are out there have variable strength, variable and suboptimal porosity. So there are lots of, and even now in research, people argue about the fact that 100 microns is the optimum size for a pore size in a bone graft substitute, and that's because a lot of, so again, thinking in your future lives about working in the third year, don't really believe everything you read in a journal publication. So a lot of journal publications will say, 100 microns is the best size for porosity in a bone graft substitute. It's because over the years, people have misinterpreted a paper written by a researcher, Klavitzer, back in the 1970s, where he said 100 microns was a good size for a pore interconnection. The pore interconnection is the size of the holes between the pores. And this was related to the fact he was working with polyethylene, and you needed to have a big pore interconnection size because polyethylene is a near inert material. You've got fibrous encapsulation of that material, and you needed to take that into account as well as bone regeneration and space for vascularization. So in fact, if you've got a bioactive material, you probably don't need pore interconnection sizes as large as 100 microns, but you do need pore sizes that are reasonably sized. You want them to be actually probably more like 500 microns or so. So don't believe everything you read in research papers. Sometimes people misinterpret things, and then that sort of becomes groupthink and gets carried on through the literature. So all of these, so you can imagine things like aluminium oxide, so dense strutted aluminium oxide ceramics, they were very, if not just resistant to remodeling, they never were going to be remodeled. They were going to stay as lumps of aluminium oxide in the patients forever. So this sort of resulted in the first generation of synthetic bone graft substitutes not meeting clinical needs. So there was a real backlash against this from the surgeon community. So the surgeons were confused by the wide range of different materials they were being pumped with, basically. And half the time these materials were highly unreliable, so they were just put off by them. So they went back to using good old traditional autografts and allografts because they knew where they were with them. So what had all of the early bioengineering and biomaterial scientists got wrong? Well, we'd all forgotten about the fact that bone is alive, but it's adaptive to environment. It's doing this, mechanotransduction and mechanosensitivity and looking at what's going on around it and then how the environment changes. And so-called bone homeostasis, so the maintenance of bone mineral density at a certain level, is an equilibrium between what we call the anabolic and the catabolic processes. So it's the resorption by osteoclasts versus the deposition by osteoblasts. And if you introduce a material or an implant or a device in there which is going to disrupt that balance, you're going to end up potentially with the reversal in bone density, which is the last thing you want. And one of the key things that's increasingly now with the sort of genomic understanding and proteomic understanding that's been developed now in the sort of fields of biology and bioengineering is that understanding that proteins have got a key role in all biological processes. So proteins are like nature's nanobots. So proteins are changing shape inside you, and changing shape for a protein is a way it controls its activity. So these little proteins that you've got, several 100,000 of them in your bodies, all the way these proteins interact with each other controls all of the functions of your biological processes, and unsurprisingly, including things like fracture healing and broken bones. So sticking implants in there that are going to influence the proteins around them, and the proteins are going to absorb to those materials and change shape and respond to them in different ways, actually had a key influence on how the different materials we were implanting in and using as bone graft substitutes actually worked. So with the failure, if you like, of the first generation of bone graft substitutes, people recognised that actually you wanted something that's going to support the native regeneration capabilities of the body. So something that's going to work with local proteins and cellular processes to regenerate bone in the vicinity of it. So sort of move from bioinert is okay to actually no, it's not. We want something to be bioactive in a bone graft substitute. So how can materials engineers achieve that with inanimate materials? None of our materials are ever going to be alive. We're not going down the world of Frankenstein, not yet anyway. So we need to think about biocompatibility. We've got materials, how can we make those materials in such a way that they become biocompatible and bioactive? So we need to understand how the material is going to respond to the physiological environment, and also how the biological environment is going to respond to the material. So given our starting point really was to steal all our ideas from nature. So this is where hydroxyapatite comes in. So hydroxyapatite has got a very similar chemistry to natural bone mineral. So it's got the same crystal structure. So it has, but the difference between hydroxyapatite or phase pure hydroxyapatite and bone mineral is that phase pure hydroxyapatite, so this is its evil crystal structure here. It's basically got phosphate ions in it, OH, so hydroxyl ions in it, and calcium, and nothing else. And phase pure hydroxyapatite has got a calcium to phosphorus ratio of 5:3. That's sort of just basic calculation of maths from how many calciums there are to phosphates in the unit cell. And if you deviate from that ratio, you end up with the hydroxyapatite decomposing and producing what we call a biphasic or multiphasic material. So you end up with different calcium phosphates or calcium oxide in there as well. Bone mineral, on the other hand, is able to have calcium phosphate ratios that vary all over the place because it substitutes in different ions into the crystal structure of hydroxyapatite. So, for instance, I've got things on there, some examples. So things like carbonate and silicate will substitute in for the phosphate groups within the structure, and sodium, magnesium, strontium, and zinc will substitute in for the calcium ions. And this is how bone acts as a mineral store for all of your important metabolic minerals and how it plays an endocrine role. So as bone is being resorbed and released by osteoclasts and osteoblasts, it's releasing also micro or nano levels of trace elements into your metabolism or into your interstitial fluids for redistribution and metabolism. So bone acts as your mineral reservoir, as well as being having its roles in strength and locomotion. So one of the things we did early on is look at what happens if we mess around or if we mess up our control of hydroxyapatite chemistry. And so we had made up some materials that had that were phase pure, so they had the calcium to phosphorus ratio, the magic 1.666 infinity. And we made some that were a little bit calcium rich, so they had a calcium to phosphorus ratio of 1.7. So this meant this was now phase impure, so it was mostly hydroxyapatite, and it had only 2% of calcium oxide in there as well. But that small amount of calcium oxide was enough to basically to stop the material from being bioactive. So with pure hydroxyapatite, you've got direct bone bonding. With the impure hydroxyapatite, you've got this fibrous interlayer formed. So it was no longer bioactive. And that explains a lot of the variability people were getting in materials from first generation when they didn't understand that you needed to be this controlled with the phase purity. So a manufacturer might have had a plus or minus 5% on the tolerance of impurities, and that would have been enough to stop the material from being reproducibly bioactive in the clinical situation. So the next thing we thought about was, what about all of the other ions that are actually in bone mineral? And there was at the time we were doing this research, we had Professor Larry Hench staying as a visiting professor. And he was the guy that invented bioglasses. So he was running around telling everyone how amazing silicate was. So we thought, okay, there's all of this evidence for silicate being really important in sort of early bone regeneration. And that with bioglasses, it was found to upregulate all sorts of BMP2, so that's a very important growth factor in bone formation. And dietary intake of silicon was linked to bone mineral density. So everyone who drinks in a glass bottle is potentially increasing their bone mineral density by increasing their silicon levels in their dietary intake. So other beers are available. So it meant that potentially with silicon substituted HA, there was lots of evidence that we might want to have silicon in the structure. So we produced some silicon substituted HA, and then we did some basic in vitro testing to look at whether or not it made a difference or not. And we found that if you just looked at cell attachments to different materials, so the blue is without the silicon and the yellow is with the silicon, there was absolutely no difference at all if you looked at the cell attachment in serum-free media, so media without any of the proteins. As soon as you introduce serum proteins to the environment, which is what you're going to actually have in the body, there was a massive difference between cell attachments. So the cell attachment on the silicon HA was much higher. So it's like, okay, so changing this crystals or the chemical structure of the material to include different ions in there influences the biological response, but only when the protein's around, which now, with hindsight, makes complete sense now that we understand that the proteins are key to interpreting interaction between cells and their matrices. So what was going on? Well, we looked at the material and characterised the effect of adding the silicon. So those of you that are good at chemistry will have thought to yourself, they're swapping silicate ions for phosphate ions. They've got different charges. So that's going to affect the charge balance within the material and its electrochemistry. And what that does is it changes what we call the point of zero charge. So effectively, the surface charge of a material when it's put in an aqueous environment is related to its intrinsic chemistry. And by messing around with the ions in the chemical structure of the material and increasing the ions, we were basically changing that sort of surface charge on the material. And that was also having an effect on the hydrophobicity of the material. So it's also affecting the contact angle. So if you imagine, if you compare a frying pan with PTFE coating on it versus a frying pan without a PTFE coating, and you drop a bit of water on there, you get the water bubbling up on the one with PTFE, and that's because it's hydrophobic. So what you want to do is actually reduce, you want to basically something to become more hydrophilic in something like bone graft substitute, because you want the surface and the proteins to interact on that material. So we found as we were changing the chemistry, we were also manipulating the contact angle and the surface charge, and thought, okay, so that must be what's affecting the proteins. So we looked at the protein absorption, and again found that there was no actual difference in the amount of proteins being absorbed to the surface of our materials until we got to 24 hours. So when you implant something, and when you look at cell attachment, all of that's happening instantly. So a difference not happening until 24 hours couldn't really explain why we were getting a difference in cell attachment in a couple of minutes. So what we did then was look at what sort of proteins were being absorbed on the different materials, and found that if we took these two time points, so this is where you've got no significant difference in the amount of protein on the materials, and looked at what was there, there were significant differences in the types of proteins that were there. And the key one that was interesting was fibronectin, and that's a protein that's critical to cell attachment. So the fibronectin was absorbing at much greater concentrations on the surfaces of the materials that were substituted with silicon. So the changes in the hydrophobicity and the surface charge of the material was resulting in more protein absorption of more of the fibronectin protein absorption, which is then enhancing cell attachment. So the enhanced cell attachment also then translated to faster cell differentiation. So the sorts of cells, so bone cells, are what we call attachment dependent cells, and they have to be attached to something in order to function and stay alive. So, and they do this through various transmembrane receptors, including things like integrins. And the integrins are key to certain types of absorption proteins, fibronectin being one of them. So by manipulating your chemistry, you're getting the right proteins absorbed on the surface. That then is presenting anchorage sites to the cells that are able to attach to them in a way that they are, for want of a better description, used to attaching on bone matrix. So then that gives them a way of recognizing the surface as something that they should be attached to. And then that was proposing them to differentiate faster and then go into bone production mode. So it's helping the osteoblasts and other types of cells, so stem cells, be pushed down an osteogenic pathway to produce new bone. Okay, so the second half of what we were doing from a materials engineering point of view was looking at the hierarchical structure of bone and again copying it. So natural bone, especially cancellous bone, is very porous, and something like a femoral head, you can see how good it is at dealing with mechanical adaptation. So if you do some finite element analysis on the top of a femur, you identify that where you've got these trabeculae lined up is exactly where the principal stresses are passing through. So your bone is very good at basically realigning itself to meet the maximum stresses and meet the loading where it needs to be. It also, within the struts, is highly porous as well. So it's got these interconnected microchannels and little spaces, which we call lacunae, for the cells to sit in. And this is a way for cells within the bone to be able to sense their environment, communicate with each other, and drive nutrient transfer in and out of the bone, which is really important. Because bone being mineralized, nutrients don't just transfer through it like they do in other tissues. You need to have strong vascular penetration throughout the material to make sure it gets the nutrients it needs to maintain its live functions. So we started looking at trying to develop a novel processing technique that would give us the ability to make porous structures with hierarchical pore structure. So is it not only porous, at the scale you can see when you look at it, but it's also the little white struts of the material are actually filled with porosity as well. So this will help to make sure that you'll get nutrient transfer throughout the structure. Okay, and one of the other things we looked at is, again, what happens if you change the total porosity? So if you imagine something being 80% porous, I think the materials I pass around are probably around 80% porous. When we were first starting to work in this area, people wanted things that were a lot more porous because they thought that they needed to be strong. So, you know, lots of materials being produced with sort of 60 and 70% porosity, and not so much around 80% porosity. One of the things I did as a PhD student is look at the fact a material which had such a wide variety of porosities, I could take different samples, characterize them, and split them into 60%, 70%, and 80% groups, and then do the analysis on how bone grew into those different groups, and found quite remarkable variation in the amount of bone volume and the rate of bone regeneration related to the porosity. And if you thought about this from a mechano and materials engineering perspective, it made sense. You've got a material, you've got a tissue that's mechano-responsive, and you're putting in implants with very different mechanical properties. So the 80% material only had an ultimate compressive strength of about half a megapascal, whereas the 60% material is more like about 7.5 megapascals. So you've got an order of magnitude difference in the strength of those materials. And unsurprisingly, the host tissue, which is mechano-responsive, senses that, and you get stress shielding occurring effectively in the more dense 60% materials. So you get a much lower amount of bone growing in there because it doesn't need to be there, because there's a nice strong material around it. And then if you do mechanical testing of the grafts after they've had bone incorporated in them, you can see that so this red line indicates the strength of control bone in the area we put the implants in. And you can see that even though you've got very different mechanical properties in your starting implants, by the end of 24 weeks, everything's statistically the same, because the bone knows what strength it needs to be. Now it needs to be the strength of surrounding control bone, and that's controlled the rate and the volume of bone that's regenerated in those grafts. What was really surprising to us, though, was the impact of strut porosity. So putting porosity into the struts of the material, which we thought were there mostly for nutrient control. We found that if you optimize the chemistry, so you use silicon HA as opposed to normal HA, and then put in different amounts of strut porosity, you could end up controlling your material to an extent it wasn't osteoconductive. So osteoconductive is where a material supports bone formation. It moved into osteoinductive, so you could implant it somewhere that there was no native bone, and you would get spontaneous bone formation occurring in the material because it's driving stem cells to differentiate down an osteogenic pathway. So we found by increasing the strut porosity up to sort of levels of 30% or 40%, we were able to get our materials to behave like it was a growth factor, effectively. So it's a dead, inanimate piece of material, but it's influencing the response from the local host tissue to act like it was an inductive material. Okay, so all of that meant that we had a lot of understanding of what was going on and how to improve things. But while doing all of that, one of the key things that we did was made sure that if we developed stuff that was novel, we patented it. And this was very important because to get things actually in the clinical environment, you have to be able to commercialize it, and therefore you've got to attract investors. So by having things that were novel and patentable, we were able to attract investors. So we got some money from 3i, and that enabled us to, launch the first commercial product. So we sort of launched a product with variable porosity initially. So sort of going with the 60, 70, 80% porosity, highlighting that actually, if you wanted fast healing, you needed to use 80% porosity. And then we introduced the silicate substitution. And then the company was bought up by Baxter. And then we then introduced the sort of the osteogenic materials as well. So we sort of introduced a sort of a raft of different materials over the years. And we were able to do this because the materials we developed, we made sure they had patent protection. Okay, the other side of things, the not so sexy side of things, potentially from a science point of view, is making sure that whatever it is you develop actually can be used in the real world. So we could have made the most amazing materials, but if the surgeons couldn't use it, no one was ever going to buy it, no one was ever going to invest in it. So it was really important for us to work as a multidisciplinary environment, to talk to clinicians, find out from them what materials they wanted to use, what things were important to them. And one of the key things that was important to them was handling. So you can imagine you've got these. So when surgeons are using them, they're sort of 1 to 2 millimeters or 0.5 to 1 millimeters inside as granules. So you can imagine you open up a packet of these and they're going to fly all over the place. They're going to be difficult to work with. So we had to use development of sort of novel poloxamer blends in order to make encapsulate or use as a polymer carrier the granules, so that surgeons can open up a packet, take out basically a sort of a putty-like mixture of granules and squidge it to whatever shape they want, and then place it in the defect site. And this is an example of an intervertebral spacer, where they put the granules in the putty, in the intervertebral spacer hole, and then that then is put into the gap between the vertebrae, and the surgeon's not having to worry about the granules falling out while he's doing that, getting that intervertebral spacer into position in the vertebra. So, what has this done in the outside world? So I guess, we've developed materials that have had a lot of now clinical impact. So the materials have basically been found to, improve things for both the patients, as well as sort of socio-economic impacts of sort of reducing costs to healthcare providers by reducing hospitalisation and operation times. So it's a sort of win-win from both the patient's perspectives and also the healthcare providers' perspective. To date, they reckon it's been used in about 400,000 patients in about 30 countries. And at the moment, around 24,000 patients have been treated a year with various materials we've developed. We've got a production facility up at Elstree, so not very far from the Harry Potter studios. And it's generating an average turnover of about $14 million a year. Sadly, we don't get a share of that. And the research has been celebrated. So it was used a couple of years ago as an example, as one of the sort of 50 years of British, or as an example of one of the bits of British engineering achievement that had been achieved in the last 50 years. So we have a stamp made up of the material. Okay, so where are we going next? Well, over the years, the sort of basic research we've done has given us more questions than answers. So we're now trying to get into really understanding the biology. So why on earth just increasing strut porosity in the material results in it becoming osteoinductive? I've got no idea, and we're trying to figure it out, basically. And in doing so, we've developed new types of perfusion and modelling systems for looking at how biology interacts with these grafts. And we're now potentially using those sorts of perfusion systems for a more personalised medicine approach. So can we get autologous grafts by putting in a basic synthetic graft, putting the patient's own cells on there, culturing them up, and then being able to implant that in somebody, so they've got even more enhanced bioactivity. And as I mentioned at the start, we're also looking at smarter biodegradable implants, so that are degrading not just as a result of the local chemistry, but also as a result of the cell and the protein interactions. Right, and all of this is very much a team effort, and I've highlighted in blue all of the students that have been involved in this research over the year. And they were both undergraduate students doing projects and also PhD students doing their PhDs with us. And you can see that, students do get to do research that actually is quite interesting and useful. So you never know. you might end up doing something with us in a couple of years' time. Okay, well, thanks for your patience at the start of this. And if anyone's got any questions about anything, feel free to ask. I'd say people online, type something in the chat if you want to ask anything. Anyone got anything? Yes?
Why is cell differentiation important?
Good question. So cell differentiation, so if you imagine you've got stem cells, so those are the basic cells that your body produces that aren't, so when you have a stem cell, it can do anything-ish, depending on which lineage it is. But if, say, a mesenchymal stem cell can go and form all sorts of different types of cells specialized to different pieces of connective tissue associated with different organs in your body. So if you are wanting bone regeneration to occur, if you can provide an environment where a stem cell comes along and is encouraged to differentiate down an osteoblastic pathway, so it becomes osteogenic, so bone producing, it means that you're not relying on cells that are already committed to being bone producing cells. It maximizes your chance of getting rapid bone regeneration, because you'll be able to tap into the stem cells as well as any osteoblasts or osteogenic cells that happen to be around. So, and that goes not just for bone regeneration. So other people, or some of the things we're doing as well, looking at applying the same sorts of principles to different tissues. If we can understand what's going on in different tissues and what encourages different tissue differentiation, if you like, or cell differentiation in different tissues, then you can do the same things across, medical engineering, basically. Anyone else got any questions? Yes?
Did you do a degree in materials?
Yes, yeah. So I did my undergraduate degree in materials. So I know, probably should admit this, but I don't actually have any formal qualification in biology. I don't even have a GCSE in biology. So I did my undergraduate, so I did GCSEs in things like chemistry, physics, maths, technical drawing, probably don't even do that anymore, and art. And then I did A-levels in technical drawing, art, physics, chemistry, maths, and applied maths. And then I did a first degree in just good old materials engineering. And back in the day, we had what we call thin sandwich courses. So it sounds hideous, but we did 6 months at university and 6 months working in industry for the first 3 years, and only had a year at university in the final year. But what it meant was by the end of it, you were minted because you were earning an outrageous fortune. So then we'd get lots of industrial experience, and that really helped with understanding. So again, I would encourage you all to do industrial placements if you can, because that's really good for helping you crystallize what you want to do actually when you leave here, which is quite important. And yeah, so it's just quite a nice way of doing things. You get a feel for what actually you might want to do with your degree. And as knowing that you don't want to go into industry is as important as knowing what you do want to do sometimes. So yeah, so I did my undergraduate in materials, and then I went travelling for a year, and then I came back and did my PhD in biomaterials, and then picked up the biology as I went along. So again, as one of the things we're trying to do within degrees here is to open up everyone's ability to think multidisciplinary and across disciplines and stuff. That's why we've got everyone in this sort of first year of everyone all together, try and get everyone to think about things across disciplines. Because increasingly, the way things are going, it's all about plasticity. There's no more jobs for life anymore. It's about being able to take your skills and transfer them to something that probably doesn't even exist yet by the time you're in work. Okay, all right. Well, thanks for coming, everyone.